very important theorem in electromagnetism is Helmholtz theorem. Helmholtz theorem states that an arbitrary vector field C of R can always be decomposed into the sum of two vector fields, one with zero divergence and one with zero curl. Here the vector C can be written as the sum of C perpendicular and C parallel. The divergence of C perpendicular is 0 and the curl of C parallel is 0. Now the vector field C can be explicitly written by the curl of another vector field and the gradient of a scalar function as equation 1.173. Now the function omega and function f should be related with C by the equation of 1.174 and 1.175, and the integrals should be converged all over the space. This result is valid for both static and time-dependent vector fields. Now, let's see why the theorem is valid. According to the definition of Dirac-Delta function, we can write the vector field C at R in this way. Now, there is an identity involved with the Dirac-Delta function, which is Laplacian of 1 divided by modulus of r minus r prime is equal to minus 4 pi Dirac delta r minus r prime. We are going to replace the Dirac delta function. So it becomes the Laplacian is in non-primed coordinate and C at r prime is in primed coordinate. So we can easily write the integral in this way, where we can switch the position of vector fields and Laplacian. There is an identity involved with the Laplacian of a vector field, which is curl of a arbitrary vector field A is equal to gradient of divergence of the vector field minus Laplacian of the vector field. So Laplacian of the vector field will be we will apply the identity in the integrals considering C divided by modulus of r minus r prime as a vector. So the equation C at r becomes let's apply another vector identity for divergence of a product of a scalar function and a vector fields, and it is if we apply the vector identity for divergence of C at r prime divided by modulus of r minus r prime, where the nabla operator is in primed coordinate, it will be and if there is a function of modulus of r minus r prime, there is a shifting property for it, which is the gradient in non-primed coordinate of the function f will be equal to minus of the gradient in prime coordinate of function f. And if we apply the properties in the above equations, we can write the last term will change. Let's rearrange the last equation. So another relation we can write here divergence of C at r prime will be 0 because the nabla operator is in non-primed coordinate and the vector C is in primed coordinate. So now we will replace this equation so that the operator in non-primed coordinates can be written into the terms with operator in primed coordinate. So it will be And this equation will help us to comprehend our integrals. Let's follow a similar step for curl of C at r prime by r minus r prime. So it will be the vector identity I used here is curl of f vector A is equal to f multiplied by curl of A minus A curl of gradient of f. Now using the shifting properties we can write so minus sign will be converted into plus as I converted the gradient operator from primed coordinate to non-primed coordinate. Now the C cross gradient of 1 by modulus of r minus r prime will be now we can also write that curl in non-prime coordinate C at r prime r minus r prime is equal to curl at non-primed coordinate